Okay, so for turning effects of forces, we are looking more as to how objects actually turn clockwise and anti-clockwise, and they tend to move. So what happens is for moments, right, is where force can actually make an object to move and to turn. And for an object to actually turn, it requires three main things. The turning effect, the force, and also the pivot. The pivot will be the angle in which you will actually result in the movement of the turning effect, and then the force will determine the direction of the turning effect. Okay, so moments will have direction, the clockwise and anti-clockwise. So clockwise actually follows the same arrangement of how your minute and second and hour hands actually move off a clock. That's why they say clockwise. However, if you are looking at anti-clockwise, it actually moves in the opposite direction. Then that will be in this manner over here. Now, moment is this quantity really depends on two main factors: the amount of force applied, which is in Newton, and the perpendicular distance in which a force can be applied. Meaning that the perpendicular distance, it must be in line must be in line of the action of the force to the pivot. So in this case, right, the distance traveled, right, would be perpendicular to the force that is being applied. You could see that there's a 90 degrees, and where it stops at where the pivot is actually exerted. So for questions that involve more than two pivots, right, you have to actually decide where will the turning effect outlast to. Okay, so hence the moment of a force that about a point is defined as the product of the force and the perpendicular to the line of the action. How to calculate moment? You just have to multiply both of these variables together. Some of you may ask, what about those kind of questions which you don't actually get a very clean cut kind of perpendicular movement. Rather, let's say this is the amount of seesaw, and the force is actually, let's say, this way. So how then what is the perpendicular distance? So the thing here is you need to first answer the question whereby what is perpendicular distance. So you can take a projector or set square, and then you actually let it slide along the line of the force. Later on, then what you do next is you mainly draw a perpendicular line. Okay? And then this would be the perpendicular distance for the force. Even though the force never really hit 90 degrees at the end of the beam, you can still find the perpendicular distance because it is 90 degrees and it ends at the point of the pivot. So the SI unit for a moment is actually Newton meter. There are some textbooks that actually put Newton centimeter, but it is not widely practiced. Instead, for your O-level examinations, you have to convert the cm to meter. So just take note, 1 meter equals to 100 cm. Okay. So there are two main types of forces, the moments of force, the clockwise and anti-clockwise. Where the clockwise moment, right, it is the turning effect that cause an object to actually turn in a clockwise manner. On the other hand, the anti-clockwise is you turning it in the other direction. And one thing to note is that the further away the force is from the pivoting point, the larger the moment of the force is required. Hence, you can actually turn an object easily. So actually, I'm not sure is it in Cambridge or Oxford. The door to their lecture theatre, it tends to be a very big door, and you tend to actually have to open the door hinge. So let's say this is the pivoting point here. Okay, and that you want to open the door inwards. Where should you push the door? Should you push the door at the side here, or should you push the door at nearer to the hinge? The answer is you should push the door further away from the pivoting point so that you don't have to generate so much of amount of force to open the same amount of direction. And how, because the thing of the it's again based on the concept of the moment. And if let's say you apply the force nearer to where the hinge is, or the pivoting point, you'll realize that to generate the same amount of moment, you will need to generate more force. So this will actually let you feel that the moment of the weight of the door is actually very, very heavy. So what we can see is when we want things to be simplified for us to do work easily, we want it to be able to generate a great amount of moment. If you cannot control the size of the moment, then you want to reduce the amount of effort or the amount of force generated. Okay? So when there's actually more than one force acting on an object that produces the same direction of the turning effect, the total moment will just have to be the sum. That means you add all of the moments together. But do take note, this is only for moment. The question never asks you to add all the force together first, calculating it with the consideration of the distance each. That is the wrong idea. Instead, this only applies for moment, meaning you have to first calculate the moment for number 1, adding it to the second moment, which is number 2, to get the total amount of moment, and then make a decision as to where the overall force is at. Okay? So you can actually take into consideration some of these working examples in calculating. Now comes the principle of moment. So for principle of moment, certain objects will have two types of moments acting on them, such as a seesaw. So this object, right, can actually turn in an clockwise or anti-clockwise direction. And when the clockwise moment is equals to the anti-clockwise moment, the object will generally stay in balance or in equilibrium. What this means is that due to the principle of moment, the sum of anti-clockwise, the sum of clockwise moment about a pivot has to be the same or equal to the sum of anti-clockwise moment about the same pivot. That means all the total moment in the clockwise manner must cancel out to the other one for an object to stay balanced. Okay, and in this case, you can be following through this formula where moment F1 times D1 equals to moment 2, which is F2 times D2. The next question is what happens if I have multiple moments acting in this direction then? So what you should do is then you should go and calculate the moment number 3 and sum it up together with clockwise moment, which is this part here, F2. So you just get another one, which is F3 times D3. And this should equate to the moment moving anti-clockwise. So in exam, you just have to be very careful in what we are actually dealing with. And one last thing that a lot of students tend to forget is the weight of the ruler. Because the weight of the ruler, the mass of the ruler also, the weight of the ruler also contributes to a direction of the moment. And usually the weight of the ruler will be influenced when the pivoting point is not at the midpoint or the middle point or the center of gravity of the object itself. So you will need to also take that into consideration in your calculation for moment, because the ruler does exert some form of moment, even if it's negligible or very small. So based on the value or calculation outcome of clockwise and anti-clockwise moment, we will then be able to identify what is the strength of the magnitude of the moment and eventually make a decision as to the turning effect or the direction of the object eventually. So these are some calculations to show how we can go about doing calculations. But do take note that the units of measurement should be always in meter and also in Newton for force, so that it is clear and easy to follow through. Next, we look at center of gravity. For center of gravity, it is the point in which the whole weight of an object seems to act on it. And in this case, what we can see is that the center of gravity tends to be quite easily identified in a regular object. However, if there's an irregular object, then you will need to know the steps to go about calculating the center of gravity. So first of all, an object can be balanced at the center of gravity only because the turning effect due to the weight of the object on the respective side of the center of gravity is counterbalanced, meaning all the moment are actually cancelling out each other, allowing it to be fully balanced. Okay, so for regular object, it's quite clear cut. We just have to draw the like let's say for a rectangle object, we just need to find the both ends connected together. And the point of intersection is where the center of gravity is. For a circle, it can be any different direction because the diameter should be more or less stable for all points. Okay, then of course you have the ruler, the triangle, that also gives you the same amount of sides for each of it. Okay, but one important thing is what about irregular object? How are we able to go about identifying the center of gravity? So one way to do it is using this concept of when an object is suspended freely in air, okay, the center of gravity will be in line or vertically underneath the hanging point of the line of action. Where the swinging point at the bottom, right, there's actually a pendulum weight holding onto it. So this is the crucial experiment that you need to know, in which what you can do, you punch hole for 3 different positions of the center of an irregular object, and from there you hang a pendulum. Next, you mark out the positioning of the line of action, which is generated by the string, and you find the point of intersection. The point of intersection would actually indicate where the center of gravity is at. This is similar throughout, regardless of the mass or the weight that you actually use for this particular experiment. Okay. Next thing, we look at stability. So stability is basically how extensive or the extent to which an object can be restored to its original position when you tilt it. And this is and when you tilt it, right, the factors affecting the stability of an object would include the position of the center of gravity and the base area. So for something to be very stable, right, your center of gravity tends to be as low as possible, nearest to the wall, nearest to the floor, so that this will actually allow the whole object to be stable. So there's some saying for very tall people, right, they tend to actually fall down easier. Like when you push the person will fall down easier as compared to someone who's very short, because they for tall people, they have a higher center of gravity as compared to short people. Next, we look at base area of support. So when we look at sumos, right, they tend to spread out their legs, and they tend to bend very low. So by bending very low, they tend to reduce their center of gravity. By extending the leg far apart, they build a greater base area, allowing it to be more stable. So it's the same concept for wine glass. For the wine glass, you could see that the base area is actually quite flat and it's actually quite big. This helps to bring a lot of the center of gravity, the base area to be wider, so that the wine glass will not topple easily. So when the line of action of the center of gravity, right, is within the base area, then the object will be said to be stable. Meaning, no matter how you tilt it, as long as the line of action of the line of center of gravity is still within the range of the base area, it will still fall back or return to its original position. However, when the line of action, right, is actually outside the area of the base area, right, the object will then actually topple down. And when the object topple down or change in position, that would actually mean that the object is unstable. One good example that we can illustrate is like the stability of a bus, whereby we could see that the center of gravity for the bus is always below the area or within the area of support. Even when there is a lot of bus movement or things like this, you will still realize that the bus is still stable in the sense that this line of action is still within the area of the support of the bus. However, when you watch like movies, then the bus actually topple when they do a very sharp turn. This is where all the mass actually started to change, and the bus will actually topple when the center of gravity is actually outside the base area. So for example, your double decker SBS bus, right? It may have a higher center of gravity, however the base area for the bus is quite high. Second thing is they also tend to limit the number of people who actually goes up to the second level, and the reason is because you do not want too many weight to be allocated at the top of the bus while below is actually vacant or what. This will bring up the center of gravity of the whole bus higher, but of course the bus has all the heavy engines at the bottom, at the first level of the bus, therefore it shouldn't affect that much. Okay, then we look into types of equilibrium. We have three main types. We have stable equilibrium, neutral equilibrium, and also unstable equilibrium. So stable equilibrium is when, right, the object, whenever you change the position of the center of gravity, when you raise it or what, it will still have a tendency to return to its original or lower position. So this is what we meant by stable. Unstable is just not like how I explained, where the line of action of the center of the gravity is actually different from the base area, and it will actually change the direction. So an object is said to be an unstable equilibrium if this center of gravity is lower. That means you from starting very high, it is later on drop down to somewhere very low. So there's that change, and this is due to the fact that the center of gravity has this tendency to take up a lower position, means the original position was unstable. Then let's look at neutral. So for neutral positions, right, the object would actually, regardless of how it moves, the center of gravity should still stay in the same level. Like for example, a ball. When you roll a ball to the left or right, you are changing the direction or positioning of the ball's orientation. However, the height of the center of gravity remains consistently the same. So that is what we meant by neutral, not stable. So stable means that I must change my position and then return back to the original position. Neutral is I change my position and I will move into a new position because my previous position was unstable. Neutral is regardless of how much position I change, it will always create a new position with the center of gravity being intact at that point. Okay, so that comes to the end of this chapter on moments, where you will be tested on how to calculate moments, what is the principle of moment, and at the same time apply your skills in calculation for more moment questions and problem statement. If not, that's all.